All right, so I want to thank the organizers for their invitation. So I have to confess that when I received the email from Alison with the invitation letter, I thought, up for a conference about the Swampland and the universe, I thought, that's maybe, I don't know, some confusion. But then actually, I read the letter and I realized that it came with a well-defined task. And the task said, overview talk on current neutrino oscillation data, cosmological bounds and tension. And I thought, okay, that sounds like me. Okay, so they seem to know what they are doing. All right, so here I am, reporting from the trenches on the status of neutrino masses, mixings, and whatever what we understand, not understand at this time. I will start with with the three neutrino paradigm that I will call, and then some explorations. And because part of my task of duty is tensions, I tried to go last night, so I don't know what happened, and everything there is a tension is a green thing, so that it flashes. All right, so, but if they don't find enough of them, I'm really sorry. All right, very good. So you have to forgive me, it's early in the morning, so I'm going to start very, very slowly. I hope I don't offend anybody. All right, so why particle physicists, when one find neutrinos to be so exciting, is because they were predicted to be boring beyond what you can imagine in the standard model, which is a gauge interaction of the as a gauge theory of the particles. Right-handed neutrinos are total singlets, don't have a place in that model, and that model possesses an accidental global symmetry. That means that baryon number and each of the lepton flavors are conserved. That means total lepton number is conserved, and that means that within that model you cannot generate a neutrino mass to any order in perturbation theory, neither non-perturbative because it's anomaly free, B minus A is anomaly free, nothing. So let me go the description of what we have observed that contradict this in a qualitative way, and I will go to the quantitative. So what we have is that atmospheric neutrinos, these are muon and electron neutrinos and antineutrinos that are produced by the interaction of the cosmic rays on the top of the atmosphere. By the time they make it to the detector, with its energies of the order of the GeV and having traveled around hundreds of kilometers, that about 50% of my muon neutrinos and antineutrinos have disappeared. And then we actually built dedicated beams from accelerators, which are mostly muon neutrinos or antineutrinos, that you know whether neutrinos or antineutrinos, and shoot them at distance of hundreds of kilometers, energies of GeVs. And again, we have seen them disappear over distances of 300 kilometers in Japan and 800 kilometers in this country. And we also seen that about 50%, okay, in some of them. So, and not out of 50%, some of them, all of them, okay, depending on the energy. So some of these, a small fraction of them, we have seen them appear as electron neutrinos, a very small fraction of them. And then we have seen that the solar neutrinos produce, the neutrinos produced in the sun, which are electron neutrinos, that's they only produce. By the time that they make it to the Earth, a fraction of them is not in the form of electron neutrinos, but it's in the form of either muon or tau neutrinos because they do interact with neutral currents in the detectors. And then we have reactor antineutrinos on the Earth, and we have seen them disappear at two very distinct baselines. Long baselines, these are MEV neutrinos, so they antineutrinos. So we have seen them over distances of 200 kilometers, or still hundreds of kilometers. This is what I will be calling long baseline reactor experiments. First in Camland for many years, and for the last 3 months, we have now data from Juno, which I will report upon. And then we have also seen them disappear on a much, much shorter baseline. Much less of them disappear on a much shorter baseline. Anyway, down to the basics of my symmetry, it means that the lepton flavors are violated in neutrino propagation, which are good news, that's the good news. We need to extend the model to account for these observations. We would like to know, obviously, what is the dynamics behind this new physics. And for this talk, I am just going to tell you the painful path of trying to find the minimal consistent description at low energy that can account for these observations. Very good. So in principle, simplest, or maybe the most straightforward or the better motivated, it wouldn't have to be, but it happened, okay? To introduce lepton flavor violation is to add a mass to the neutrinos. And for the neutrinos, unlike for the other fermions, I can do this two ways. In the most minimal way, I just don't add any state. I just take my left-handed neutrino and realize that the charge conjugate is a right-handed field, so I can make a mass-term. And this is what we call a Majorana mass-term. The mass eigenstates of this operator are their own antiparticles. Total lepton number is violated, but most importantly, the gauge invariance is violated because these are parts of a doublet and the other part is not there. So that clearly means that this mass term can only be thought of as a low energy realization of some high dimension operator. I'll come back later. The alternative is I introduce these singlets and I couple them through Yukawas to the left doublets, and then I introduce that is what we call my usual mass term, like any others of the fermions, and then I have to suppress the right-handed mass of the Majorana mass. And that means that I'm not only adding the right-handed neutrino, but I'm imposing a total symmetry. So my total lepton number now is not an accidental symmetry, it's an imposed one in the theory. And in this case, my neutrinos are like any other particles, any other fermion. And either way, for the point of view of what I'm just trying to describe, I introduce lepton flavor of passive violation because I can have, this allows for leptonic mixing in the charge current interaction of the leptons in similarity to the CKM of the quarks. It's different, slightly more general, because since right-handed neutrinos are free, I can add as many as I want. So in principle, my leptonic mixing matrix doesn't even have to be 3 by 3. It could be 3 times n. Okay, so that's what we do when we add light sterile neutrinos. We extend the matrix that way. But anyway, but either way, as I said, this phenomenon tells me that flavor is not conserved in neutrino propagation, and that goes under the name of neutrino oscillation, flavor oscillations. And what it means is that if I produce a neutrino with a flavor alpha and I detect it after a certain distance L, that neutrino can be detected with a flavor beta, beta being the same or different as alpha, with this probability that oscillates in L over E. And that's important. This is the characteristic dependence of this oscillation wavelength with energy is what points out to masses as the mechanism for the flavor transition that I have observed. When I started in this business, we had to make sure that what we were observing is the effect of masses. And that was the way. Other new physics would also induce oscillations, but will change the energy dependent of the oscillation wavelength. Anyway, this is the general expression within massive neutrinos. It oscillates in L over E with an amplitude that depends on the mixing angles. And this term, this is the probability for, let's say, neutrinos. And if I would like to write it for antineutrinos, I would have to change U by U star. And if you're starting off for this, you see that this doesn't change and this will change sign. So this is the term that will characterize CP violation. So in order to quantitatively, or more or less quantitatively understand, or qualitatively, what I'm going to describe you have to understand when in any of these experiments, I'm mostly sensitive to a given distance and a given range of energies. So that means that a given experiment is dominated, the effect in a given experiment is dominated by a particularly delta M square. So if I go in this two neutrino limit, my probability takes this very simple form. I only have dependence on one delta M square. I have a dependence on one single mixing angle with a very specific form. And just that's how I usually detect it. I'm going to measure observables as a function most of the time of the energy. And this way I can locate the maximum or the minimum. And that will tell me the delta M square. And the amplitude will tell me the mixing. And but the important thing is that in these dominant effects, the dependence on the angle and on the masses is such that I do not have information of the ordering, I do not have information of the octant of the mixing, and I don't have signals of CP violation. So these are three things that in vacuum oscillations entered as when I embed this in the more general, more than two neutrino scenario. So the dominant effects are not sensitive to this in vacuum. It's a little bit different when neutrinos cross dense matter, like what happens in the sun or in the crust of the Earth for these long baseline experiments. And in this case, what happened is that the neutrino can forego and forward the scattering, totally forward scattering. All right, total coherent. That's a coherent effect that you describe by introducing a potential, what we call the matter potential, that neutrinos feel when they travel through the matter. And the interesting effect is that because matter has electrons and doesn't have muons or taus, that potential is flavor dependence. So that affects the oscillation pattern. And I don't give you the expressions, but the important thing is that it affects in such a way that you gain dependence on the octant and you gain dependence on the the delta, the sign of the delta m square. So you gain dependence to the ordering or octant, depending how you want. And that is what we have observed in solar neutrinos, which give us the dependence of the mixing angle in the solar neutrinos. And in the long baseline experiments, it helps us, is fundamental to find the sign, what we call the sign of the delta, the relevant, and the octant also. Very good. So this description, so down to the basics, what we have seen in all this data, which I'll come to the quantitative, but we have seen this phenomenon. We can characterize this phenomenon with two distinctive delta m squared, hierarchically going by more than one order, almost 2 orders of magnitude. And we have amplitudes that need 3 mixing angles, okay, which are very different and large, relatively large. And we have convinced ourselves that what we are seeing in solar neutrinos is the effect of these conversions because of the matter potential. Very good. So just to put the frame of the parameter space I'm exploring, if I have the minimum that I need, there's 3 neutrinos to explain 2 delta m squares. So this is the way in which we parameterize the leptonic mixing matrix. And these are the Majorana phases that you will have in addition if neutrinos were Majorana, which we don't access with neutrino oscillations, but I'll come back in a minute. And so it's there are many ways in which you could have chosen this parameterization. This parameterization was chosen this way because this way the 2 neutrino dominant pieces on each of the experimental pieces are easier to identify. So it's convenient. But for convention, all the mixings are between 0 and 90 degrees. The phase, the CP phase, the only CP phase in the problem is between 0 and 2 pi. And by convention, 1 delta m square is positive, the small delta m square is positive, and the third state I can put it above or below, and that goes under normal ordering or inverted ordering. And this is, as I said, this parameterization, it is easier to identify which is the dominant effect in each of the experiments that I told you, and it helps you to keep track of where the physical effects come from. It's convenient. Very good. The other piece of information that this table tells you is that obviously non-experiment is able to address the full parameter space. In order to actually address this parameter space, you have to combine data, and that is combination that is in the hands of phenomenologists. I am one of the people, founder of one of these groups, and we call ourselves NuFit. And to put it clear, the task at hand is this is all the data that I will show you, and down to the basics. And we build our own likelihood for each of these experiments. We do not import likelihood from experiments whenever we can. So with the exception of these 2, so that we build our own, our better understanding of which systematics have to be included, which theoretical uncertainties have to be included, and we try to obviously get as close to the experimental results as possible in their analysis, but we have our own way of testing things in our chi-square. And these 2 things that I'm putting here are atmospheric neutrinos, experimental results, the latest result from Super K and from ICECube, but mostly from Super K. ICECube eventually will have the information. For Super K, there is no way to reproduce what they are doing. They just simply do not give you the data. So you cannot make a chi-square of a data that you will have. So we can invert their table. So I will be showing the results if I do add or not add that table, because it's, I cannot verify that table. What I will happen, I have till 2023. For this one, it's just simply they still did not give us the enough information on the effective areas. But we will get it. No. This we will get it. Okay, it just takes time. this, and there's a lot of interaction. We have a lot of interaction with the people from S-Cube, so that's not the problem. Super K is a different story. Anyway, so this is the results of the global analysis in the three-neutrino paradigm. And I'm showing you these are the all parameters, 3 mixing angles, the 2 mass differences. This is the one that by default is positive. This is the one that is positive or negative. And along my talk, blue is inverted ordering and red is normal ordering. And so this, I'm showing you the chi-square as a function of this. And for those of you who don't fit, that the minimum tells you what is determination at a certain level on this tells you the confidence level at which you can determine. And if this looks very parabolic, that means, oh, beautiful. And if it doesn't, then okay. And there are full lines, which is the analysis without this external table from Super K, and the dashed line, which is the analysis with the external table of Super K. I will come in a minute. So what I see here is these 4 parameters are beautiful. I have well-determined 2 mixing angles and the small delta m squared, though I will come in a minute to a little tension there. That's what I call time by tension. And the module of the large is well defined, okay? But, okay, so now.
So what do you mean by the percentages there?
Is this. Is if I put 3 sigma up, but the 3 sigma out divided by 3 times. So this is my, I don't put 1 sigma, because at 1 sigma there's still, so to get an idea of the 3 sigma sensitivity, the 1 sigma sensitivity, I take the 3 sigma, I divide by 3. Because it's not exactly 100% Gaussian. So this is somehow a little bit a more conservative way of defining the 1 sigma uncertainty. So, and this is in the modulo for the large mixed angle because the ordering as, okay. So the mixed angle 2, 3, which is the large one, it's still just saying it's maximal, not maximal. It is, okay. It's not robust yet. And then the difference between the height of these 2 curves, between the blue and the red, points out to whether I'm favoring or not favoring inverted or normal. I'm coming about, so what do we know about the ordering? And then this is what do we know about the CP violation. And these 2 effects, these 3 effects are extremely correlated in the data. Okay, so this is, I have been doing this for more than 20 years, but since 2012, we decided to put our efforts a name, NuFit. So nobody sometimes tells me, who are you? And I say, who is my name? They don't know, but I say, I'm NuFit, and they know who I am. And really, I am NuFit, because I have a web page, and I'm the owner, personally owner of that web page, which actually, I was giving a talk in front of a funding agency, and say, what do you mean you are the owner? I mean, what if you die? That will be a problem. I say, yes, to me? Okay. Certainly to me. Okay. So, but anyway, there was no way within the bureaucracy of at the time to actually fund this webpage, and now it's okay. So now I pay for the next 100 years, all right. Anyway, so when I look at this table and I see what is the progress we have done since the last, I don't know, 15 years, it's kind of, there was a lot of progress the previous 10 years, but the last 15 has been kind of slow, the progress. So well, it's painful to gain precision with neutrinos. And so I say, I don't know if I should jump out of the window when I look at this, but I do other things. This is not the only thing that I do with my life, all right? So, I mean, this, please, but somehow I'm always invited to talk about this, okay? So please, invite me to talk something else. All right, so, and the red thing is what we really, you see, where the most of the confusion is at the moment. I should have put also red here. Very good. So let me tell you a little bit of where the action is. Yes?
Because didn't you have that for the inverted hierarchy in CP in the previous plot?
Yeah, but unfortunately, this is when you are in the normal ordering.
Oh,
and that is 3 sigma divided by 3. 3 sigma divided by 3.
Okay.
Yeah. Okay, so it is, all right.
So could you go back to the plots? So I'm understanding this right, that these plots, they prefer a little bit better normal order?
Yes, I'm coming to that. Don't worry. You are going to hear everything you want about this in the next 2 slides. You may be sick of it at the end of my talk. All right. Anyway, so here we are. So let me go, before I get to that, to the one of the things that somehow has been popping up in this analysis continuously, which is when I go to this 1-2 sector, it's called, I'm comparing the determination of these oscillation parameters from the solar neutrinos, these are the regions, with MSW, so that clearly points out to this octant. of the angle, so I'm below 45 degrees. And the determination from these long baseline reactor experiments at the time only Camland. And you see there is a certain mismatch. It's nothing, it's about a 2 sigma tension. It was a 2 sigma tension for many, many years. And I don't want to do this, but down inside, it comes to the, it's are effects in solar neutrinos, which you don't see the turn up of the MSW strongly enough, and you don't see enough, you see too large the ignite asymmetry that pushes this region down. Okay. The thing is that this is something, both effects that are associated with propagation in matter. So people were thinking, maybe I have some hint of new physics in this matter potential, which if I get there, I will tell you. Well, so in the last 5 years, the solar neutrinos have moved a little bit. We also have better determination, better fluxes for the solar neutrinos. And now we have Juno. So that is the Juno main effect of the last 3 months. And believe me, getting this region affected my Christmas vacation. Okay, so I am attached to it, and I will come back to Juno. But anyway, so what you see now is that because of this, the effects of in the solar has changed a little bit. The tension now is down to 1.5 sigma, but you still have this kind of intriguing different. I have more reactor experiments. I have Juno, I have Camland, and I also have Snow Plus, which is less precise at the moment. But all of them point out to a delta M squared, which is different than the one that is favored by solar within the precision. So the best fit, there is a mismatch of around 1.5 sigma. Do more or less that. I don't incorporate this in the analysis is done, assuming that this can be combined with no problem. But it is, you have all the slides in Zoom. Anyway, so now going to your ordering. Very good. So we have information in the current data on the ordering of the states from different sources. So let me walk you through them. The most obvious way is by looking at this electron appearance in muon in long baseline experiments. That's T2K and that's nova at that 2 different baselines. So there is this is okay. So the sensitivity here enters through the different matter effects in the propagation of these two in these 2 cases. So this is T2K, this is nova. This is a simplified version of the data too, so that you understand what is happening. This is the total number of events observed as an antineutrino and neutrinos in T2K and nova. The shade is the data. The gray is the data. The curves are the prediction whether in normal, blue, normal, red, blue, inverted, and the shading is changing theta to 3. Very good. And this is as a function of delta CP. Fantastic. So you have to see where these are. And these 2 predictions are more separated in nova than in T2K because nova has a longer baseline. Okay, qualitatively this is very clear. So now if I look at this in T2K clearly, you see that it is merely here clearly, and it's compared to that, I have a preference for normal ordering. But the red is overlapping better with this. And the delta CP, which is almost maximal. Now if I go to nova, I also have, it's less obvious, but I also have a kind of better, mainly here and here, you see, better with normal ordering, right? But now the delta CP that I'm favoring is totally different. And this is in the same convenient. Anyway, so each of the experiments seem to favor normal ordering, but there is a 2 sigma tension in the favor delta CP. And then again, where is the 2 sigma tension? Is something that has to do with propagation, so people think maybe there is something again in the potential in the Earth. And we, in our fit, we combine this data because we convince ourselves that the tension is not so bad that they are going to be. But clearly, because I have this tension, when I'm going to say something about CP violation, adding the rest of the data is going to be very different if this data helps me in this direction than if the new data helps me in this direction. Okay, so depending on where I go, the situation with what I know now about CP violation is going to depend.
What could explain the tension? Assume the tension was real. What kind of new physics could it explain?
Yeah, so I got back. So people talk about non-standard interactions, and if I get there, I will tell you about it. And yeah, so we are. If I get there, we don't see that, but Yes, so if you just look at this data and you don't worry about the fact that if you put something new here, it also show up somewhere else. So you have to be consistent. That's the name of the game here. And if you don't care, the people put non-standard interactions with, and then that will, okay, I will come. Dimensions 6 operator of neutrinos interacting with the matter.
The CP violation is parameterized with one phase or three phases?
No, in the neutrino oscillation, only one phase enters.
So it's the same derived and major?
Yes, because this is a total, think about it, it's a total lepton number conserving process. So how would you know? How would you know?
So with inverted ordering, the delta is better determined,
Yes.
even though you're saying it's less, better, less.
And then I've layered, as long as I'm only looking at these two experiments and I combine them, this is the favorite solution. But when I add more, I'm losing. And when I'm losing this solution, then I'm gaining confusion in the side. Okay, very good. All right, so what additional information I have in my data? I told you, if I want to go beyond, to go to CP, either, I have matter effects, or I also have, because of 3 neutrino effects in vacuum. So I can have CP version ordering. I can have effects of ordering by, if I look at the dominant oscillation wavelength in muon disappearance in vacuum versus electron disappearance in vacuum. Once I introduce the subdominant 3 neutrino effects associated with the little delta m squared, those effects are different. The relation between these two quantities are different in normal and in inverted. So by comparing what muon disappearance in long baseline tells me versus what electron disappearance at the medium baselines tells me in reactors, I can gain some insight on this. And that is what I'm showing in this figure. This figure is busy, and you may not see this, but if you do it quantitatively, the agreement between this, which is the determination of the large mix, the large delta m squared in muon disappearance, between the determination of the large delta m squared in reactor medium baseline experiment, is better, the agreement is better here than here. Okay, that, believe me, okay, I will show you the curve in a minute, but the point is that once I include this data, now I am moving my preference slightly towards normal ordering. This looks like a soap opera, but that's it, okay. All right, so appearance at long baseline because of this tension, inverted ordering favored, CP violation maximal. I add now the information from effects in the comparison between disappearance in reactor and the long baseline, and I recuperate the favoring of normal ordering. That's why this red curve is lower when I had than the blue. It's a small effect. But once I'm here, then again, I can have CP violation with much less determination. And now comes the table of super K. Ta-da. And if I add the table of super K atmospheric neutrinos in the table prefer normal ordering even more. So that push the difference at C. And I separate this data because this effect, and that's what I'm trying to illustrate here, is well beyond what they should be seeing. They are seeing an effect that is well beyond their sensitivity. Okay, and that's their own paper. And also, them to the right in their data analysis, which I cannot reproduce because they don't show me the data, there is some kind of tension with both. So that effect is not robust, I would say. Okay, so that, but anyway, at the level of what we are, normal ordering is slightly favored.
They say that in the paper? That
Yes.
There's an effect that is better than it's expressed in their paper.
Yes. They also say that, but they also say, look at this, it's really not that great at the fit in any of the two. Very good. So my conclusion of this is that these effects, the ordering, the octant of theta to 3, CP violation, are correlated. They are subdominant in the present experiments. And to dig them out with certainty, we are going to need new experiments, all right? And the first one that is coming is Juno, that is already come, is Juno. So let me tell you what Juno has showed us. All right, so this is Juno. Juno is disappearance of reactor antineutrinos and at a distance of 60 kilometers. So the dominant This is the survival probability where you have the big oscillation wavelength is because of delta m squared 1, 2, and these little wiggles are the delta m squared 2, the large mixing anchor, the large delta m squared. So they are sitting here, so their dominant effect is this. And then they do have, with enough precision, they aim at separating these two seeing the difference between these two in the little wiggles. So this is their data as after 50 days. And in their paper, they smear out this. So I have included this data in our analysis, and in our analysis, what I'm calling 6.1, because they smear it out, we smear it out in our official analysis, because they, ordering is a national issue in China, and you don't want to get the Chinese upset. Anyway, so we don't, but now nobody prevents me from looking at the data. All right, so this is what you do when you look at the data. We have this paper that we look at the data. So this is the curve that you have with the effect. This is the dependence of the chi-square of Juno with this mixing. This is inverted and this is normal. So you see, by themselves, Juno still do not have precision to tell me the difference between these two effects. But I can see how much is compatible with what I know from everywhere else. So I'm adding Juno to this time of information of relation between disappearance and muon and electrons. All right, and you see here that clearly it's better the agreement with in the normal than in inverted. And the reason why this is not incorporated is because obviously if I shift this a little bit, this changes, and this shift is associated maybe coming from systematics, and they have not given us enough information to make sure to put my hand on the fire. This is. On the other hand, with what information they have given me in their resolution, blah, blah, I reproduce beautifully their main results. So somehow we cannot be too bad. So this cannot be too far from the answer. But if this is not too far from the answer, then normal ordering is getting a boost. Okay. All right, and how we go from there? We need a new generation of experiments, and that is then besides going farther with Juno, then the best we can do is to build this new generation of long baseline experiments, Dune and Hyper-K, and this is from this European particle physics brief book. I was participating on this working group, and I can tell you, getting the experiments to agree on this is not easy. So the fact that this is here and there's some years there, you can, this is, but look at the years, all right? So it's gonna take time. It's gonna take time. All right, good. All right, so now we go to the mass scale. And all right, so neutrino oscillations do not tell me anything about neither Dirac or Majorana nor neutrino mass scale. For that, I have to go to other sources. The most robust, and I'm going to repeat this, the only robust determination that you have on the neutrino mass is from the tritium beta decay experiment. This is a kinematic effect that you cannot hide. A mass is a relation between an energy and momentum. You cannot hide that. If the neutrino is there, mass and mass, eventually the endpoint of the spectrum of tritium beta decay should be affected. This has been searched, and the present bound from the Catherine experiment, which is amazing, has been amazingly, it took time, but it's amazing how they have progressed, is 0.45 electron volts. And they are going to improve by, in a couple of years, maybe, or a year, not a long time, there's some, maybe coming, to 0.2. And to go beyond that with this terrestrial type of kinematic effects, you are going to have to wait, and there is not a clear approved experiment to improve over that. Okay, so that is a fact. Then you have, if you want to know neutrino, if Dirac or Majorana, your best probe. Yes, you wanted? The best probe is neutrinoless double beta decay. That only happens if neutrinos are Majorana. These are the best lifetime bounds on this process. And if your only source, if your only source of the lepton number violating in your model is the neutrino mass, then there is a connection between this and something that we call the Majorana neutrino mass. But there is an if. They have to be Majorana particles, and this has to be the only source of this break. And then you have, and then these are the bounds from the most precise one from Kamlan-Zen. And this range is not that there's the observed, it's that the bound can be from here up or from here up, depending on nuclear matter elements that go into the calculation of this. Yes?
Can you go back to the previous slide? So the mu-e there,
What?
this is a bound on the electron neutrino mass.
In the effective electron-neutrino mass is called.
Okay, and how's that related to the mass
Here,
someone else?
here.
Oh, okay, got it, thanks.
Okay?
Okay, good, thanks.
Good.
And that's different than what you're calling M-E-E.
It's a different, which is this one. So here, as you see, the U is not in the modulus, so faces appear, the Majorana faces appear here. That did not appear in the other one. It's coming. Here you have it. This is the answer. If I am dealing with 3 neutrinos, and since I know the 2 delta m squares, and I have a relatively well-known the mixing angles, I have a prediction of this as a function of the light state. So I have, what I don't know is the scale, the lightest scale. Other things I can reconstruct. And then we have cosmology that we are coming, and it is mostly sensitive to the sum of neutrinos. Very good. So,
In the previous slide where you were showing, yeah, exactly, atoms, like if you, for instance, assume that there's a Majorana mass that they come from CISO, is this putting a bound on the heavy neutrino mass scale?
yes, so if you put that, but it's also constrained by the mixing, so depends. Usually these effects can be very small. So yeah, you have, depending on the type of implementation of the CISO. But yes, right hand, heavy states that are mixed also contribute to that. All right, so anyway, the name of the game here, and this you have seen this plot many times, what this plot is showing you is that I can plot each of these probes as a function of the lightest state, the prediction that I know from the observed, this is just taking my chi-square and projecting it from oscillations, projecting it on this two. And obviously there is a difference between whether the projection is done in inverted on the normal. And this width here is because of the Majorana phases. That's why it's so fat. I could also do, because one observable versus the other, and usually this is what you are seeing most these days. The basic message here, from what I'm going to tell you now, is that from this, if you are in 3 neutrino mixing, you have a lower bound on the sum of the mass of the total neutrinos, which is 58 milli-electron volt or 98 milli-electron volt, depending on the ordering. Very good. All right. So let's go to cosmology. Okay. And so this is the light neutrinos in the cosmology. We have usually 2 different distinctive effects, and we parameterize it by an F, which will be the it's the effective number of light neutrinos contributing, of light neutrinos contributing to the early universe in the form of radiation. And then we also have this, the total mass of neutrinos, which tells me the contribution of the massive neutrinos, but light massive neutrinos today. And we have 3 main probes. Nucleosynthesis, which is mostly probing an F, and then CMB and larger scale structure, which probe depends on both. Very good. All right. So this is very quick because I'm going to run out of time, big time. All right, fine. So anyway, so let me just, this is I borrowed this and this is my primer. So I'm talking about now the effect of these light neutrinos in the observables. And these people made an interesting exercise, which is telling me that there are 2 effects that neutrinos do. One is the background. It modifies, if you have neutrinos, will modify the expansion of the universe, and that has impact. And then the fact that because they are light, they will have an effect on the growth of the perturbations. And this is what we call the free streaming. So the basic message of this is that in the CMB, which is what I'm going to start discussing first, the main effect that being observed at the moment comes either from these background effects in the low multiples or the lensing effects the variation, the modification of the lensing effects of affecting the high multiples, the weak lensing effects are high in the back multiples. The photons coming to us get lensed. And get lensed by a structure. This is the effect on the larger structure. So you get that if neutrinos get massive, you have less structure form at the scales. And that is also part because of the free streaming and partly because of background effects of the contribution to the neutrino to dark matter. Anyway, the point is that this goes down, this goes up. Okay, so that is important. And the second thing is that you have the position of this BAO that you can detect. And that position has nothing to do with the mass. It's very, very mass independent. But it helps you to constrain other parameters that are correlated because the dominant effect in CMB is very anti-correlated with the Hubble parameter, which, as you can imagine, causes problem. All right, so this is the effect of massive neutrinos in the CMB. And we have this bound. This is the bound if I'm only considering the effect of the low multiples. And it is a rather robust bound. And then you have an improvement on the bounds when you include the full CMB spectrum, CMB multiples. And the point that I want to point out here is that this is what is called Planck PR3, and this is Planck PR4. And this is supposed to be more data than PR3, but the bound goes to worse. And the reason for that is because these samples have a tension. Without neutrinos, this data in Planck tends to have too much suppression of the lensing, of the high multiples because of the lensing. They observe too much lensing. To parameterize this, you put some normalization for these lensing effects and you let them fit the data, and you prefer a lensing that is considerably higher than one. So since that will deplete the higher multiples. Since neutrinos tend to enhance the higher multiples, this somehow increases the bound and artificially imposes a bound, increases the bound on the neutrinos and on the mass of the neutrinos. And that you can also parameterize by allowing in your fit. This always imposes that the neutrino has to be positive, the mass. You can see this tension by allowing, and most tensions that are coming, by allowing the mass to be, to put a sign, what we call the sign of the mass of the neutrino, which really means that you put a sign in front of the contribution of the neutrinos to the energy density. Yes?
Why in the last line, that is the most recent analysis, and gives you...
But because this...
PR3.
Okay, so the P3 has this tension. And because this tension, this parameter is not put in this analysis. So if I don't put it, this tension forces me, tells me I should have more lensing that I have. Since neutrinos tend to give you less, that pushes the bound of the neutrino to stronger.
Yeah, no, I understand. I said, why they didn't use the most recent...
Yeah, so this is... Okay, because I'm trying to explain. So some of them use one, some of them I'm going to tell you one thing that I had forgot to tell you, that I don't do cosmological analysis anymore. I did in the past, and I ended up finding them very frustrating because unlike what I was told you about oscillation, this analysis is a black box. Each experiment gives me a chi-square and it just summing tables. So they give me a table, they give me another table. They give me a likelihood function. I can modify the theory, but I cannot touch the experiment. I cannot play with the systematics or with the other things. So this is what you get with the likelihood that they give you for PR3, and this is what you get with the likelihood for PR4. Okay, that is it. But I'm just telling you that people, what you can do is you can play with this, and that's what you do by trying to play the systematics by either adding this lensing parameter or allowing the mass to become negative, and then see that your fit, you are pushing, your fit really when you are here is really wanting an unphysical negative mass. So that tells you have a tension in the experiment. That becomes more obvious when I am really well. Okay, forget it. Okay, yeah. Just I don't get it beyond the 3 neutrino, I think. Anyway, so this gets even more complicated when you are in adding the BAO results. There, if you just combine the BAO results with the CMB in lambda CDM plus massive neutrinos, you have a bound, okay, that it is about 64 million electron volts, which if you see, I told you this is a lower bound. I told you that in 3 neutrinos I have to be here. So that basically the obvious conclusion that I have is that, okay, adding this, I have clearly the normal ordering is in trouble. And I call this naive because if I go and I look and I do this kind of exercise, I realize that in this lambda CDM and I allow for this effective mass to be negative, there's really, what this is telling me is that I have a tension, that really, it's not that I have a bound, that really I would prefer that the neutrinos contribute to the energy of the universe with opposite sign that they do. And that is somehow telling me that there is a physical tension in the data, and that is another way of looking at the tension that we saw yesterday from the talk of Desi. And it is a way of looking at it is that if you are in lambda CDM, your Hubble parameter as favored by VAO and the Hubble parameter favored by CMB are not agreeing with zero masses within lambda CDM. It's another way of looking at it. So that's why you need to shift the masses to negative values. So we saw that the solution for the tension is to move into this evolving dark matter. And once you do that, this tension gets resolved and your bound gets weakened. So within this evolving dark matter, the bound on the total sum of neutrinos is total compatible with, from the analysis of CMB plus VEO is compatible with everything. Yes?
So would the varying neutrino mass in time help it in?
Yeah, yes.
It was lower during.
Yes, I'm coming. Yes.
Oh,
Yeah, that will help. Yes, it will help. Yes.
Oh, wow.
Okay. It will help. It will help to this. Yes, it will not help to other things. Okay, let me come in a minute. All right. So once you start going there and you add more data samples, then there are trillions of analysis, and some of them, depending on which data samples you put and the specifics of how much you open your hand on the cosmological model, you get from people who are pushing the bound to still being jeopardizing inverted ordering, to others that even claim that they have seen an effect. Okay, and so that brings me to the elephant in the room, which is what happened with these cosmobounds and the Hubble tension. The Hubble tension is this tension between the determination of the expansion rate, the Hubble parameter as measured from CMB and the VAO, and that from supernova luminous curves. And these also go under as early probes and late probes. And basically what you are seeing, as I told you, if you look at the lambda CDM, there is a clear anti-correlation between the Hubble parameter and the effective mass. And DESI by itself is already pushing this. And if you are looking at even if you would want to include this Hubble parameter from the supernova, that will basically rule out totally. That will basically tell you that my physical masses cannot be there. But the problem is not the phases. The problem is the model. So the problem with this is that this is a slide that I borrow from this talk that I really recommend this by Julian in neutrino in Invisibles, and he had this paper that made a sample of possible solutions to the Hubble parameter tension, and you don't find much. And this is the one that helped in the tension between the DESI, between the BAO and CMB, but it doesn't help here. All right? So if you want to account for that, I don't know what you do. But this is the thing about this. We have this tension in cosmology, and all the bounds that are being derived on the mass of the neutrinos are just ignoring this. So you have to assume that what you have, whatever the solution is not going to affect those bounds. And that is, okay, that's where I take the fifth. But if you want to forget about this and you still think that you would like not to have to go to other you want to still believe that you may have a problem with this, with the cosmological bounds on the total mass and the physical mass, then there are ways to eliminate, to go down this bound, and there's a bunch of references. And many of them go as mass varying neutrinos in certain way. All right? There's an
How much and what way exactly?
the references. Okay, go and look at them. There's a lot of. It's in the Zoom, right? So you have this is I mean, I give all the credit to Miguel that has actually made this. Okay, so these are, you either reduce the mass, change the mass with time, or you somehow dilute the abundance of neutrinos in the universe, and this is a bunch of references for that. All right, so this is my conclusion, and in the last 5 minutes, okay, give me 5 minutes just to tell you where we stand with the sterile neutrinos, and that's it. Okay, so do we have more information on the BSM besides this? So this is my conclusion. You can read them at the end, but as I say, 0.45 electron volt that goes to mass, as we say in Spanish, and the Cosmo bounds are subject to all this, and as I say, so let me tell you what are we standing in our quest for, or our testing of the possibility of new oscillation. So when we talk about beyond 3 line neutrinos, our main motivation as a phenomenologist was what they call the short baseline anomalies, which I'm going to describe in a minute. But to describe them, to explain them, you needed a basically gap delta m squared of the order of 1 electron volt, which implied that I had to add some new state, and it had to be sterile because it shouldn't couple to the Z. So the evolution of these anomalies go as follows. The first one is the one that was observed in short baselines in LSND. It's the oldest one. Observed appearance of mu and TNE in these characteristics, and it was a 3.8 sigma, and this is as old as the moon. Then Minibund, which was an experiment that was built to test this anomaly in a totally different environment, found its own anomaly, which both of them could more or less be described within what we knew of all the other experiments by oscillation with relatively large mixing angles with this fourth state and a delta m squared of the order of electron volt. And now comes microbund, which is pretty much the same setup. It's a different detector, but it's a pretty much the same setup as minibund. And finally has produced the result. So we don't have to go to femtobund, as I said, because they have pretty much excluded that. So they do not confirm these anomalies. They do not confirm them. So whatever it is, it's not sterile neutrinos. All right? The other anomaly that I'm going to talk about was the reactor flux anomaly. And that is a theorist-created anomaly. We have all these reactor experiments at very, very short baselines. And they had always thought they observed what they expected. Then what they expected is the expectation by a computation of a certain reactor fluxes. Now, they come in 2011, do different calculations of reevaluation of the reactor fluxes that gave us higher fluxes. So now what happened is that all these experiments, what we have found is a deficit because my prediction has gone up. So this was between 2 and 3 sigma, depending on how you compute this thing. And if you want to explain it in terms of oscillation, it could be maybe electron volt square, sterile neutrino. Very good. Now, very recently, and with more and more precise determination of the composition of the reaction of the fusion rates, the actual flux of uranium 2035 has been reduced. And once you include this new reduction in the new fluxes calculation, that anomaly disappears. So it went and go. And the last one, which is screen, okay? The last one is what we call the gallium anomaly. This started being observed when you do testing of the gallium experiments for solar neutrinos with a radioactive source to test the efficiency. What you saw, you put a source next to the detector, and you have a certain calculation of the expected capture rate. And what we also observed was systematically lower than what was predicted from my nuclear physics that I know and people, okay? And this then came, so to test that, we made a dedicated experiment called BEST, which confirmed this. And this is between 6 and 5, depending on your uncertainty on your nuclear model. But this is a big uncertainty. The problem is that if you try to interpret this in terms of oscillations, you run on all type of bounds. This is Catherine. If you have a 1 electron volt square that makes it with the nu, that would modify the endpoint of Catherine, and that has not been seen. And this has nothing to do with oscillation. This is a pure kinematic effect associated with an electron, but that needs to be mixed at that. And that is this red curve, this green curve. And then, of course, there was also solar neutrinos data. So at the end of the day, what I need to explain this in the terms, in framework of an sterile neutrino, it's really not seen in other experiments. All right. So this is the... okay.
So it's only Catherine or there is another one?
This is Catherine.
No,
There are all reactors experiments also are not seeing this, and this is solar, and I played a lot with solar neutrinos, and I told you it's not the sun. I told you, don't blame it on the sun. It's not the sun. This curve does not move. This is solar neutrinos that clearly kills all the whole region, and you cannot move it much playing with the sun from what we know of the sun. Very good. So this is where we stand. This is unconfirmed. This is this is resolved to me. And to me and to many other people, and this is unresolved and there is green. And I cannot tell you more about, so let me just one curiosity. So then NF, I thought if I have more sterile neutrinos, that will also contribute to the expansion rate, and I have impressive bounds from cosmology. And let me just a curiosity, this is the latest result from Big Bang nucleosynthesis, which is amazing, it's just very recent. I really did my homework for the task. But I found this, which I mean is criticized, but this is a Japanese experiment, Empress, and amazingly enough, they found a 2 sigma deficit on the number of hits. Yes, so believe it or not, okay, there is, not because of that, but because people it's easy to increase the number of NF in the early universe. You put almost anything will give you larger NF. To decrease is not so obvious. And then I go to my friend, and he made this beautiful compilation of ideas to decrease NF. And really, believe me, I mean, my task didn't make it to read these references, but I leave it for them to you if you feel interested on how you can actually make to decrease the effective number of relativistic species in the early universe.
So the number of relativistic species is correlated with the neutrino mass, and is correlated with H0. So at the beginning, you criticized the mass bounds because of all these correlations. So how are we trusting this one? Why do we trust this one?
Well, this is BBN, right? So this one is very little affected by your cosmological model. Right? These ones you may play, you move around, and this is where you go when you expand. Okay, this is how it gets affected by the extension. So you see, yes, that's like that. But these ones are very little affected by the cosmological model. Okay, so somehow I would say this, which is why this is so impressive. This paper is Olive and collaborators, and it's really an impressive recent paper on the number of tracks. These angles and that. Okay, so this is the helium abundance and the way that you go from what you see to what you extract. It leads a lot of processing, and there is criticism there was even there's actually a workshop at one of these flash workshops at CERN. If you're somebody interested, I can send you a link, where they are going to be discussing this. Actually, there was an early one in which they. So if you are interested in this, you may join. But anyway, so the difference is the actual sample of stars that are looked for to extract the helium, the primordial helium abundance. You have to go from what you see to what you think is primordial, and that the processing of that is where all the all the thing is hidden, and the experts criticize this. I'm not an expert to criticize. I just put it there because otherwise this table looked really so boring. That said, let me put some green there. Okay, so this is the. All right, so I am going to stop here. I had many other slides if you are interested in how you go beyond the sterile neutrino. And but I think I should stop here, and I will let you read, and we can talk about it.